representing a matrix, we would generally use uppercase letters, so capital A, capital B, capital C, and so forth. We will denote the ij entry. I represents the row number, j is the column number. That's just A sub ij. Right, so for instance, A sub 1, 1 would be the entry in the first row, first column. So the m by n matrix would be represented this way. And so this matrix, m rows, n columns. M by n is called the size of the matrix or the dimensions of the matrix, and it's always row by column.
So then why do you use I and J?
I and j are just placeholders for a specific row. So n is the total number of rows, whereas I would be the row number that the entry's in. Right, so if we're looking at this here, I would be m, j would be n. And that would be the m comma n entry. So it's just standard notation. We always typically use I and j to be indices. However, this notation can get really tedious really quickly. 100 by 100 matrix. Have fun writing that matrix and proving stuff about it. So we shorthand it and say that the matrix will just be in square braces a sub ij, or in parentheses a sub ij, to represent an m by n matrix. I stick with the square braces.
Is the capital letters for the entire matrix and lowercase for like the specific?
The entry, yes.
Okay.
Right, so this notation you're going to see a lot in theory. So let's look at vectors. Calc 3 people. Actually just did vectors in Calc 3, so that's fun. A matrix that is a single column. Right, so n by 1 is a column vector or just simply a vector. Specifically, it's an n vector. Right. Physics, intro mechanics, 3 vectors are what you work with the most. Really, it should be 4 vectors. Time. Physics works in 4 dimensions, time, and 3 spatial. To get string theory, then it's 10 vectors. There are also row vectors. So 1 by m would be a row vector. And vectors will be represented with a bold lowercase letter. But vectors are just special matrices. Right, so vectors you can still work with as a matrix. Matrix arithmetic. So you're given two m by n matrices.
You'll need to unlock your iPhone first.
No, I don't. Go away. They're said to be equal if aij is equal to bij for each I and j. That is, the two matrices are equal if they have the same size and corresponding entries are the same. Given an m by n matrix A and a scalar k, the matrix Ka, k times A, is the scalar product. It's a scalar multiplication. And you just multiply each entry in the matrix by the scalar k. Given two m by n matrices A and B, the matrix A plus B, which is the matrix of entries Cij, where Cij is Aij plus Bij, is called matrix sum, matrix addition. So when you add two matrices, all you do is you add the corresponding entries.
Same size to do.
So that's what I was going to ask. Can you add any two matrices together? They do have to be the same size.
Okay.
If you try to add two matrices of different dimensions together, it's undefined. And notice then that the sum, the matrix sum, has the same dimension as well, right? It'll also
think about multiplication?
I'm going to get there. Now, subtraction. It's not an operation. There is no such thing as matrix subtraction. It would just be, if you had A minus B, it's defined as A plus negative 1 times B. So that's why there's no matrix subtraction defined. That's true in general. In arithmetic, you only have 2 operations, addition and multiplication. Product of 2 matrices. Be nice if you just multiply corresponding entries together. Nope. You're given an M by P matrix A and a P by N matrix B. The product, A times B, is the matrix of entry Cij, where the ij entry is the sum from k equals 1 to p, aik times bkj. This is matrix multiplication, and your product is m by n.
Is this the dot product?
It's not a dot product in matrices, but you can think of it in terms of dot products. And in fact, when we're using Wolfram Mathematica, you do have to do the dot operation for matrices. Matrix product is only defined if the number of the number of columns in the first matrix is the same as the number of rows in the second matrix. All right, so if you just look at the sizes, your middle numbers have to be identical.
What happens if they aren't?
Then the operation is undefined. So this should be very easy to see just from that. AB, does it equal BA? Nope. You've now lost commutativity. In fact, in this specific example, BA would be undefined. Your standard order of operations still holds. So if you're dealing with multiple matrices, multiple operations, you still use PEMDAS. A new operation, transpose. Transpose of an M by N matrix A is the N by M matrix A transpose. And notice the only difference. Your columns and rows switch. So the ij entry in A is the ji entry in A transpose. Which means the resulting size is n by m. Algebraic rules. Each of the following is valid for any scalars alpha and beta and any matrices A, B, and C for which the indicated operation is defined. So we're assuming that your matrices A, B, and C will have the appropriate sizes. Matrix addition is commutative. Right? A plus B and B plus A are the same. It's also associative. So you maintain commutativity and associativity for matrix addition. As was already stated, you lost commutativity for matrix multiplication. However, you do maintain associativity. So the grouping doesn't matter. AB times C is the same as A times BC. Matrix multiplication does distribute across matrix addition from the left. Right, so this is a left product. It also distributes from the right. Remember, you've lost commutativity, so you have to have two distributive properties. Scalar multiplication, the order in which you do the scalar multiplication doesn't matter. Right, so you can do alpha times beta first, or you could do alpha times the scalar multiple beta A, or you could do the scalar multiple beta times alpha A. Some of these properties are proven in the video. I don't know how many. I don't remember how many. The rest obviously left as an exercise. This one is actually pretty useful. If you're multiplying two matrices and one of the matrices is a scalar multiple, you can just factor out that scalar. So the order in which you do scalar multiplication for a matrix product doesn't matter. Alpha times AB is the same as alpha A times B, which is the same as A times alpha B. And a natural extension of this would be if both A and B are scalar multiples. Right, then you can factor out both scalars, take their product, then do the matrix product. So matrix scalar multiplication does distribute across addition, scalar addition. It also distributes across matrix addition. This one should be pretty obvious. The transpose of the transpose is just the original matrix. If you take the transpose of a scalar multiple, it's just the scalar times the transpose. Right? So the transpose of a scalar is just the scalar itself. Transpose of a sum is the sum of the transposes. So transpose distributes across matrix addition. Right, this is what everyone wishes normal exponents was. And a plus b to the fourth, be nice if it was just a to the fourth plus b to the fourth. Sadly, it's not. But transpose does work that way. If you take the transpose of a times b, it's the transpose of b times the transpose of a. So you distribute the transpose through and flip the order of multiplication. Those are the basic operations on matrices. There are still a few more we're going to be looking at. So we've been talking about scalars, right? Scalar. 3 would be a scalar, right? Pi is a scalar. Be careful. Incorporate my favorite number in there. Is that a scalar?
It's a null set, so wouldn't it technically be a vector? Or I mean a matrix?
So this isn't null. I know where you're getting null from. That's phi, the golden ratio. But yeah, that's a 1-by-1 matrix. That is not a scalar. Right? They are not the same thing. So you have to be careful with notation. That is matrix multiplication, which, depending on the size of A, would be undefined. Right, that's a 1-by-1 times A, which means A would have to be 1 by, and it'd have to be, what is that, a single row. It would have to be a row vector in order for that product to be defined. So just keep that in mind. We're given two matrices, and we want to find two evaluations, a plus b and 2a minus 3b. Let's first determine the dimensions. Right? So what you typically now want to start doing, whereas before you would see, oh, you know, here's a value a, here's a value b, I want their sum, you just blindly go in and do a plus b. Or I give you a value a, value b, and I say find a, b, a times b. You just blindly just go in and do their product. Now you actually want to check to see if it's defined. There's nothing worse than spending some time trying to do something that is impossible to do. What are the dimensions of A?
3 by 2.
You reversed.
2 by
It's 2 by 3. It's always number of rows by number of columns. Right, so there's 2 rows, 3 columns. That's 2 by 3. What is the size of B?
Also 2 by 3.
Would their sum be defined? Yes. If you take the scalar product of a matrix, does it change its size? So the other operation would also be defined. Both of these are defined. So now we go about finding them. Let's see if this seat is high enough. Ah, it looks okay. Except there's this power strip here. Move it like this. This is where graph paper actually is beneficial when dealing with matrices. It does let you keep the matrices nice and organized. Sadly, I don't think I have an option for that. I view grid lines. Yeah, they're too large. That's a shame. Guides don't help either. So we're going to have to just deal with matrices that probably do not wind up being straight. A plus B, remember when you add matrices together, all you're doing is you're adding the corresponding entries. So the 1, 1 entry would be the sum of the 1, 1 entries. Right, 1 plus 3. And now it's just a matter of preference on how you go. So do you want to write matrices column by column or row by row? It doesn't matter. I typically do row by row, although I've started to get into the habit of doing column by column. Just allows me to keep everything nice and centered, the columns nice and centered. Because you start dealing with matrices that instead of have constants, you have functions. Differential equations. And advanced statistics. So I'm going to stick with column by column, actually. 2 by 1 entry would just be the sum of your 2 by 1s. And 4 plus negative 7. This up here is your 1, 2 entry. Negative 2 plus 0. Your 2, 2 entry. 5 plus 1. Your 1, 3. 3 plus 2. And your 2, 3. Negative 6 plus 8. And now that's just first grade arithmetic. Or prenatal arithmetic. 2a minus 3b. Two A. Multiply each entry in A by 2. I think what I'll do is this. Just so I don't have to rewrite it. So theoretically speaking, this is not 2a minus 3b, it's 2a plus negative 3b. Arithmetically, it doesn't matter, but I will write this as plus and then multiply every entry in b by negative 3. Look, I just went to my old habit, doing it row by row. Yes, the advantage of electronic notes, you can actually highlight your ink and do copy paste, so you don't have to rewrite the same bloody thing over and over and over. And I'm not going to write out the sum of each entry like I did last time. Now we just add the corresponding entries. So what is the 1, 1 entry?
-7.
What about the 2, 1?
29.
1, 2. 2, 2. 1, 3. And finally 2, 3. And there would be our results. So nothing too terrible. In fact, this is basically a repeat of top 3, isn't it? Just with more entries. One of the rare occasions you can fall asleep in one class and not miss a bloody thing. Nah, that's enough with numbers, numbers are boring. Let's do some algebraic equations. We're solving for x, y, z, and t. Implies Left-hand side, do the scalar multiplication. And of course, scalar multiplication is always defined. That is how the left-hand side simplifies, right? Now fully simplify the right-hand side. Is the right-hand side defined? Yes, it's 2 by 2 plus 2 by 2. You get what? X plus 4. Z plus t minus 1. X plus y plus 6. And 2t plus 3. What does it mean for two matrices to be equal? Two things have to be true. First one,
Same amount of rows and columns.
same size, same dimensions. Are they the same dimensions? Good. Now, what's the second condition?
Each input value needs to be the same.
So be careful how you word that.
Yeah.
And corresponding inputs or corresponding inputs would have to be identical. The 1, 1 and 1, 1 on both sides have to be the same, which means 3x has to equal x plus 4. Go away. And the 1, 2 and 1, 2 have to be the same. And your 2 1s have to be the same. And your 2 2s have to be the same. All 4 of those statements must be true. Oops, I don't want to title. Let's write that like that. Right, so typically you'd see this written not like that. Be written like that. So from algebra, I think it's algebra 2. Redo systems of equations. Or maybe it is algebra 1. Algebra 2 is redo systems of inequalities. Either way, this is a system of equations. Let's try and rewrite these so that we have all of the unknowns on one side. We get 2x equals 4 for the first equation. Negative x plus 2y equals 6. 2z minus t equals negative 1. T equals 3. Oh, that's nice. Right away, we get values for x and t. X has to be 2, t has to be 3. Using that knowledge, we now have those two. Negative 2 plus 2y is 6. 2z minus 3 is negative 1. What's y? 4. What's z? 1. There's our solution. And of course, you can always verify that by plugging in your values and verifying that that is a true statement. Matrix multiplication. What is the size of A?
2, 3.
What is the size of B?
3, 4.
Is the product AB defined?
Yes.
What's the size of AB?
3, 3.
A 2 by 4. And it's just the outer numbers. So that is useful to keep in the back of your minds to make sure that you actually write out the product the correct way. And so now I have to think back to how the product was defined. So start the 1, 1 entry. If we come back, notice you keep the row of the A the same. It's only the column that's changing. And you keep the column of B the same. It's only the row that's changing. Since we're looking for 1, 1, I is 1, J is 1. So we look at the first row of A and the first column of B. And then multiply the corresponding components that way. Right? So it'd be A11 times B11 plus A12 times B21 times A13 times B31. That would be your 1, 1 entry. And you have to do that for every single entry. And there are 8 of them. Yeah, this sucks. So until you get the hang of it, if you think in terms of vectors, think of row 1 of A as a vector, column 1 of B as a vector, take their dot product. That's your entry. 2 times 2 is 4. 3 times 1 is 3. Negative 1 times 4 is negative 4. So I'm going to go column by column. Going to keep the first column of B, but now look at the second row of A, and then do the same thing as their dot product. 4 times 2 plus negative 2 times 1 plus 5 times 4. One, 2 entry, row 1 of A, column 2 of B. 2 times negative 1 plus 3 times 3 plus negative 1 times 1. And we're going to continue in this manner for every entry. So it'll be 4 times negative 1 plus negative 2 times 3 plus 5 times 1. So there's the 2, 2 entry. Next up, 2 times 0 plus 3 times negative 5 plus negative 1 times negative 2. Four times 0 plus negative 2 times negative 5 plus 5 times negative 2. Two times 6 plus 3 times 1 plus negative 1 times 2. 4 times 6 plus negative 2 times 1 plus 5 times 2. First row, 3, 6, negative 13, 13. Second row, 26, negative 5, 0, 32. And now just make sure that that's the right size. Is that 2 by 4? So there's the product AB. What if instead it asks for BA? What was it? It's undefined. For the sake of time, I'll skip this one.
So in order for it to be defined on the last one, the column and the row have to be the same.
Column of B has to be the same as the row of A, which is why this one would be undefined, right? You have 4 columns versus 2 rows. So undefined. We'll just look to see if these two would be defined. A, B, and C, all the same size. What are they? Right, they're square matrices. I haven't talked about square matrices yet. That's next time. But what's their size? 3 by 3, all of them. So is AB defined? Is AC defined? What are their sizes? Also 3 by 3. By the way, in this case, is BA defined? Yeah, it would be. And CA would also be defined, right? But that does not, of course, necessarily mean that AB and BA are going to give you the same thing. Same thing with AC and CA, they may not be the same. Oh, this one's going to take a while. Find the transpose of A. What's the size of A?
2, 3.
What is the size of A transpose going to be?
3, 2.
What is the first column?
1, 7.
Is that for A or A transpose?
A,
A transpose, say the first column is 1, 7.
oh, that's
Gotta be the first column.
maybe 1, maybe 2, 3.
And then the second column.
7, 8, negative 9.
And that's all there is to the transpose. Just really nice. Yes.
What function does the transpose serve?
So it's useful, for instance, if you think of the matrix multiplication as a dot product of vectors. So it'd be essentially, if you think of each row as a vector, each column is a vector, it'd just be this times dot transpose of that. Outside of that, honestly, I don't know. I can't recall using the transpose in any of my applications. Doesn't mean it doesn't. I just don't recall it. So probably not use that often. It can be useful for certain things, not necessarily the transpose itself, but writing a transpose instead. So if you want to write, for instance, a column vector or a row vector in like a computer program, it's usually easier to write one or the other. So what you do is you just enter, for instance, let's just say it's easier to write a row, but you want a column, you just enter a row, define a row, and then say it's the transpose of that. That's probably the most useful application. So really for computer programming.
If transposing is an order of operation, then where does it sit within MDOS?
Be an exponent.
Exponent.
All right, so for instance, when you do, if I go back to the properties, here, you take the transpose of each matrix first and then multiply. What is the size of B transpose? What is B transpose? First column. Second column.
2, 4, 5.
Third column.
3, 5, 6.
What do you notice?
It's the same thing.
That's the same matrix, isn't it? This is a special name. That's called symmetric, which I'll also define next class. This is where it becomes really useful. So for a lot of programs, it's actually easier to write a column matrix instead of a row matrix when you're coding. So you define it as a column matrix, and then whenever you wanted to refer to it, you just take its transpose. Right? X transpose is obviously just going to be a column instead of a row. Oops, that's -3. I'm pretty sure if you use any kind of computer algebra system in differential equations, you don't have to deal with transpose. Simply because of the way that multiplication works. It's really weird. And what's going to happen here?
It's just one row.
So our column vector becomes a row vector. And be careful with your notation. They are not the same thing. When you write a row matrix, you do not want to separate your entries with a comma. That represents something completely different. What we're going to do is verify that 13th property. Notice I used the word verify. That is not the same as a proof. Right here, what we're doing is we're saying for these two particular matrices, the property is true. That doesn't necessarily mean it's true for all matrices, right? That's the difference between a verification and a proof. So how do we have to tackle this? Let's look at the left-hand side first. We first want to find b times a, and then take its transpose, right? What is the size of b?
2 by 3.
B.
2 by 2.
Size of a.
2 by 3.
Is b times a defined?
Yeah.
Yes. 2 by 2 times 2 by 3. The result is what?
2 by 3.
2 by 3. The one entry would be 7 times 1 plus 8 times 4. And so 7 times 1 is 7, 8 times 4, 32. 39. No, I'm going to erase that for now. Next column, sorry. Right, it's 2 by 3, not 3 by 2. So it'd be 0 times 1 plus negative 9 times 4. Oh, that's nice. Just negative 36. Fourteen minus 40. Zero minus 45. Mistake in my notes, it's perfect. 21 plus 48. Zero plus negative 54. Now take its transpose. That is the matrix that we want to store in our memory. Now doing the right-hand side. We first need to find A transpose and B transpose. A transpose. That's right, that should be a negative 45. What is a positive 45? I think it's hard. B transpose. What is the size of A transpose?
3 by 2.
What about B transpose?
2 by 2.
Can you do their product? Yes. What is the size of their product? We're off to a good start. BA transpose is also 3 by 2. So first row, first column. 7 plus 32. 39. 14 minus 40. 21 plus 48. Yeah, that should be 26, right? Zero plus negative 36. 0 plus 45. 0 plus negative 54. Are they the same? They are. Therefore, we verified that BA transpose is A transpose times B transpose. A little smiley face, because it worked. If it didn't work, we'd be in trouble. Questions so far? And pretty easy so far, right? That's nice. Wouldn't it be nice if the first exam was just a bunch of transposes? We'll see how nice the RNG gods are. Maybe you'll get several, maybe you'll get none. All depends. Oh, I just go by whatever the RNG says. I sometimes mix it up if it starts to get too boring. I'll start to look for a really interesting problem to throw on. Like, okay, this is getting to be too easy and too boring. Let's find a really fun one. Calculus, that usually involves physics. Not so much for linear. Or quantum mechanics uses physics. So I could throw a quantum problem on there. And so don't forget, your initial post is due tonight. Your responses will be due on Monday. The first My Lab homework is up. Right, it's on the stuff that we just did today, just basic matrix stuff. That will be due before class on the 30th. That's next Thursday. Right, so you will have 1 week. I should be careful. The end of the semester, you may have less than a week on the last assignment. And don't forget that your project is due the 18th of February. Okay, so you should probably start working on that. Have a good weekend.